So yeah, I'm Tom Hall, not a Tarsier. I work for, if everybody who's got working internet access and a fast-ish laptop that doesn't mind their lap getting a little bit warm, could go to the address on the bottom, and if you could tweet it to your friends as well, because the goal of the talk, or a goal of the talk, is to actually evolve a genetic algorithm in your browsers during the talk, which is causing me some problems because I couldn't get wireless sorted on this laptop until about 3 minutes ago, so excuse me if the images here aren't downloaded. So I'm that Tommy Hall on Twitter. I work for a company called Forward in Camden. We host the London Node user group. If you want to come across, there's a meeting. Somebody's been there. Sorry, anybody who's been there will have seen this talk perhaps, but there is a new example, so it should still be interesting for you. So Shift Apple F. Okay, sorry. So today I'm talking about evolving genetic algorithms in the browser. So moving on, genetic algorithms are part of a category called evolutionary computing. So I'll explain genetic algorithms in a moment. Genetic programming is where you take the syntax tree of a language, most often Lisp, because the syntax is actually quite simple, and you kind of grow and evolve a program to solve a particular problem. Neural nets is, again, biologically inspired. Quite often, people will use neural nets in conjunction with genetic algorithms, which I'll talk about in a moment. So the first three are ways of solving your problems using biologically inspired methods. And the fourth one, artificial life, is a way of using computers to get insights into biology. So A-life is more about finding out things that are useful in real biology, and the other three are about finding out solutions to particular problems you've got. So in genetic algorithms, what you do is you encode a particular solution to a problem as a genome, and then you have a collection of them, a population, and you breed them. And the particular breeding algorithm I use is just to pair two genomes, choose a split point, and take the left-hand side of the split point and join it with the right-hand side of the other one, the left-hand side of that one, and the right-hand side of that one. So you actually you don't actually do the sort of piecewise random pairing that you would do in biological evolution. So as I say, more inspired than following it in detail. So they're very useful, genetic algorithms. They're particularly useful if your fitness landscape for your problem is as many hills, and you're trying to avoid getting stuck on local maxima and something. It's a very good way of exploring the solution space. Often the solution spaces are huge, and you want a way of finding a good solution in something like a reasonable time. So they're not a magic bullet. Skinner from the Algorithm Design Manual says the sort of voodoo optimization technique, and he's a little bit disparaging of it. So it's definitely not solid that genetic algorithms are the answer to all problems or whatever. But I think they're a very interesting way of solving some problems. Has everybody gone to the site I said? No. Awesome. Oh, we've evolved it already, it looks like. I'll show you what this means in a moment, but it looks as if we've got a pretty good solution. Sorry. So yeah, the two examples I'm going to talk through are from a book by Mel Mitchell from the Santa Fe Institute, Complexity: A Guided Tour. Very, very good book. It goes into much more detail about this stuff, plus lots of other stuff, chaos, some stuff about complexity theory, and a few other things, which is really nice. So I've spoken a little bit about how one does genetic algorithms in general. So you find a way of encoding a particular solution as a string, and then you have a population of them, a collection of them, and you then take them, and you select the good ones, and you breed them, and then every generation, your population changes, and the hope is that over time, your population converges on a good solution. So the problem is trying to get it all in your browsers now. how do you do that? So trying to kind of farm out the computation to you guys. So what I adopted was something in the literature which is called the island model. I haven't done it entirely. What the island model does usually is have separate populations and then have cross-pollination between them. Now, because the nature of the connection is that you're connecting to my server, not each other so easily, I've actually adopted a slightly different way of having one superpopulation that grows and grows and grows so that none of your computation's wasted. I give you 200 genomes to select, and then you go and evolve them for 10 generations and then tell me the results, so you send me back 200. The population I hold in the server grows and grows and grows and grows to a point where I've got some heuristic that says, right, shrink it again. So it's a kind of like a homegrown island model-ish type idea. So the problem that you're solving right now is called Robbie the robot. So Robbie exists in a 10 by 10 grid. His task is to pick up rubbish. He's actually can't see the whole grid. So I've said he's myopic. He can only see 5 squares. He can see the squares up, down, left, right, and the square he's currently on. So there's 3 to the 5 different possibilities. So the genome is just a string. His whole strategy is basically a lookup table. So at any point in his life, he can see 5 squares. He goes, north is a can, right is a wall, north, right, I'm mixing my metaphors. Up is a can, right is a wall, down is a wall. So my action is, look up in the table, I do this. And the things he can do is he can stay put, which doesn't help him very much. He can move up, down, left, or right. He can choose to pick up a can. It's very important. It's not like Pac-Man. He doesn't have to pick up a can if he moves through it. And we'll see later that's actually really useful for him to have something like a memory, because he has no memory here. It's a state machine, basically, 243 different states he can possibly be in, and his action is determined. Oh, I'm very sorry. One other thing he can do is to move at random. So he can do either up, down, left, right, or one of those at random, or pick up a can, or stay still. So he's given 200 moves as fitness function, because that's how we decide how good a particular solution to our problem is. His fitness function is 200 moves in this, repeated. How many of the cans does he get? If he hits a wall, he gets 5 points deducted. If he gets a can, he gets 10 points. If he picks when there's no can, he loses a point. So the max fitness is around 500. So with all you guys logged in, we very quickly reached there. The first time I ran this, it actually took 8 hours on my laptop at home, and the first time I saw the first time I saw him evolved, it was like a Frankenstein type moment, and my girlfriend was teasing me about how excited I was about my creation. So I'll show you what he looks like. How many times do I need to click exit full screen? I'm sorry.
Up? Is there an option in the menu?
Thank you. Thank you, got it, cheers. Okay, so what he actually looks like is this. So in a moment, some will appear. Interestingly, remember, he can only see the adjacent squares. He can't see the whole board. And if you notice, sometimes he chooses to not take some of the rubbish, and it's quite interesting. He'll move away from it, and that's the only way it can have any memory. And as you see, he's very, very successful. This is a fitness 500, so on average, he nearly always gets nearly all of the rubbish, and as you can see, he follows the trails of rubbish. But sometimes, and I hope we see it, sometimes he chooses not to, and it kind of gives him a memory, and he can then sweep back and grab them. So very, very successful algorithm for solving this particular problem with the constraints of that he can't see the whole board. So I was quite excited the first time I saw that. I think it's brilliant. Oh, I wasn't expecting to clap him. If you want to visualize the one that you've actually evolved, you can take the genome. Now, modulo symmetry, it's going to be exactly the same. I'm not very good at UI, so it's actually just if you just add it as a hash param thing, this will simulate now the particular one that we've just evolved. Now, modulo symmetry, it nearly always gets the same solution. So if you look, he collects them all up, and he just circles the board, sometimes clockwise, sometimes anti-clockwise. And an extra little late adaptation, just to finesse that final little bit, is he has an anti-affinity for one of the bounding walls. And that wall can be any of the 4 walls as well. So do you see there the anti-affinity? If you think about how that helps him get a few extra boxes, and if you also have a think about why he can't have an anti-affinity for all 4 walls, and there's some discussion about whether he could actually do 2 out of the 4, but I think he could do 2 out of the 4, but I've never seen him find it. I say him, obviously I'm anthropomorphizing, it's just a lookup table. So I have to watch out. Yeah, my favorite contemporary philosopher, Dan Dennett, has a thing called the intentional stance, which is basically like you have to you talk about it as if it had like goals and desires and stuff, but just hold in the back of your mind it is just a lookup table. Okay. Yeah. But some people who see it think that he can see the whole board as well. That's how successful the algorithm that is discovered is. I'm sorry, I'm going to step through this again, excuse me. This is a bit of a clumsy presentation. Cellular automata is the next example. I hoped to have it ready to evolve in your browsers today. I haven't, but I have got a simulation of a reasonably good solution to the problem I'm going to describe. So cellular automata are, I like to think of them as toy universes, and in particular, you'll see why that's not a ridiculous analogy. The most famous example is the Game of Life by Conway. I hope you've seen this before. If not, have a look at it. The thing I've showed here is a so-called glider gun. So the configuration, and just briefly, the Game of Life has rules where you can see all of your neighbors, and depending on how sparsely or densely populated it is, you live or die. But the interesting thing is the structures that persist in the universe. So this diagonal thing coming here is a so-called glider, and the thing at the top is a glider gun. So this is actually a structure that, within the rules of the Game of Life universe, emits a stream of gliders. Now, people have built, well, not actually built, proved that you can construct a universal Turing machine inside this world. So this world is rich enough to embed a universal Turing machine, i.e. can compute any computable function, i.e. like formally as powerful as your iPhone or a Cray supercomputer or whatever. And there's nothing more powerful, that it is somehow maximally powerful. So the toy universe we're going to look at is a one-dimensional cellular automaton with the edges identified. So if you've ever seen if you ever played Asteroids, the torus idea of asteroids, the edges are mapped. So cell 100 and cell 1 are neighbors. So it's a ring of cells. And the algorithm is to try and get majority voting. And again, these cells are going to be myopic, so they can only see a certain radius around them. In the particular case, they can see the 3 to the left and the 3 to the right, and remember that it wraps. So what we're asking the rules to do, again, this is just going to be a lookup table, because every cell it knows itself and it knows its 3 neighbors. It's ultimately going to be just a lookup table, and we're asking the automaton to perform majority voting. So we're saying, can you, from the initial configuration, can you get to, if the initial configuration was mostly alive, can you be, after some number of iterations, be all alive? If it was mostly dead, after some number of iterations, can you be mostly dead? And the interesting thing is, and why I say it's a bit like physics, is you can draw the history as a space-time diagram. So every row is one generation or one time increment of our universe. And as we go down, we see these interactions take place, and then by the end, it is all black. I can't remember the name of this. This is the algorithm implemented on this example, which The address is, if you go to ca/display, you can choose a particular simulation. So if we refresh it, sorry, the interwebs are a little slow for me. If we refresh it, it will do again. And we say like it looks a bit like a physics. If you look, you can see the edges wrapping. So this and this are the same. And what has basically happened is a particle theory has appeared inside the universe. So there's some, like the speed of light imposes a limit. And if anybody's done any special relativity and you've seen the light cone type idea in terms of like causality extending forwards in time, there's only so fast that information can travel through this universe, and it's determined by the width of the cells and the time increment. So actually a physics appears in the universe, and they take advantage of it to do this majority voting task. If you're curious, you can actually add the number of cells. So the algorithm is reasonably good. I've chosen to do this around the most interesting case, which is 50%. So you see the more interesting behavior when there's a 50-50 chance of alive or dead cells. And as you see, it does a reasonably good job of getting to the point where it's made a determination about the initial configuration. You can actually, if you're feeling a bit pathological, go up to 2001 cells, which gives me great joy, actually. It might not you. There you go. How wonderful is that? Particle interactions on the toy universe we've created for ourselves. So there's a sort of well-defined physics appears inside the universe, which I think is pretty amazing considering the lack of inputs, and we've only again every cell is basically just a state machine. There's only I guess 2 to the 7 different states it can possibly be in. One of the best things last time I gave this talk is loads of people read the book and it was brilliant. So there's a little bit disjointed, but another great book about evolutionary computation is a book called Blondie 24. Now, I read this a few years ago and it kind of ticked over in the back of my mind. The chappie uses the evolutionary ideas we've spoke about, but the phenotype from his genotype is the weight for a neural net. So he evolves the weight in a neural net. So a very common use of evolutionary computing, or genetic algorithms in particular, is a really good way of expressing, of getting from the genotype, just a sequence of bytes, to a particular solution, is to implement a neural net and use the bytes to describe the weight. Now he very successfully, and quite a few years ago, if you consider the computing power when he did it compared to now, we could probably do this in a few hours in our browsers. Makes a checkers playing program, so drafts or checkers, and he does normal alpha beta pruning, standard game playing algorithm with the static evaluation function as a neural net, and then evolves it to be like with no guidance, to be a top level computer checkers player. So I found that quite interesting. Last time I gave this talk, my plan was to, while I was in Kenya, read this. I got distracted by a closure book, so I've still not read it yet. I did read a little bit of it though, and I think it might be well named a new kind of solipsism, because if you read it, Wolfram thinks that he's the only person in the universe, and he's invented everything in the whole of science as far as he's concerned. So that was a little bit off-putting, to be honest, the kind of authorial tone. But this is very, very much, if the idea of a digital physics or that cellular automaton and the richness of behavior intrigues you, then this is like a 1,200-page book where he categorizes all of the 1D automata, plus moves on to other stuff. As I say, I've only dipped my toe in, find the authorial voice a little bit not so warming to me, but the effort is commendable. I'm nearly running out of time. Oh yeah, if you're the sort of person who buys people drinks at conferences and whatnot, like, I've just last week ran the Liverpool Marathon. I'm raising money for a charity called War Child. And the week before that, I climbed Kilimanjaro, so I've been a little bit busy the last few weeks. If you're the sort of person who likes to buy people a pint, you could do this instead. I'm going to wind up there. Sorry, it was a little bit confused. This isn't my laptop, and I was struggling with the presentation and trying to get the internet sorted. Thanks for your interest.